Let me introduce our final speaker for today, Margaret Mitchell. Margaret and her research team have published a wide range of papers that address such fundamental issues as the mitigation of bias in training corpora using adversarial learning techniques, and how the notion of fairness has changed over the last 50 years in specific social and technical contexts. She was one of the organisers of the first ACL workshop in ethics and natural language processing, which took place in 2017, and it's already been mentioned a couple of times. And the emphasis in her research frequently falls on the need for technologists to recognise the social impact of the systems they design and build. In one of her recent papers, she writes, and I quote, "By concretely relating fairness debates to ethical theories and value systems, we can make discussions more accessible to the general public and to researchers of other disciplines, as well as helping our own machine learning fairness community to be more attuned to our own implicit cultural biases." So yours is the last talk of the day, but very much not the least. And we're very grateful to you for travelling such distances to be here. So
yes,
over
thank
to you.
Thank you so much. I also really appreciate that opening. That's actually not an opening I wrote. You actually wrote that specifically. That I really appreciate that. It's very kind. Yeah, and thanks for having me. Cool. So let's get started. The talk I'll be giving today pulls on a ton of work from a ton of different people. I tried to sort of capture them all here with their pictures. I don't think I got everyone, but it's been a group effort with lots of influences. Okay, so if you haven't seen this before, just shout out, what do you see here?
Bananas.
Bananas. Okay, what else?
Stickers.
Stickers, what else?
Shells.
What?
Shells.
We got shelves, yeah, what else?
Banana skins.
Banana skins, I don't think I have banana skins, that's a good one though.
Reasons for leaving the EU?
Yeah. So, like, there's a lot of things you could say here. You could say bananas with stickers on them. You could start getting into embedded clauses, you know, bunches of bananas with stickers on them on shelves in the store, you know, kind of combining all the basic facts that we've said already. But we don't tend to say something like yellow bananas. You got close by saying bananas with skins on them. So given something like this, we might say green bananas or unripe bananas. Given something like this, we might say ripe bananas or bananas with spots. If you're me, you might say bananas that are good for banana bread. But given something like this in the real world, when we come across it, when we talk about it, or even when we're looking at an image and talking about it, we don't tend to say yellow bananas. And the reason for this is because yellow is prototypical for bananas. The idea of prototype theory extends back to at least the early 70s from Eleanor Rosch and colleagues, who hypothesized that there was some sort of centralized notion of objects and items in our real world alongside their attributes, the things that we expect of those objects. And when we sort of look at the world and talk about it, we access that stored knowledge and tend to only speak to and remark those things that differ from our expectation. There's some disagreement in the literature about how exactly it's stored, but the basic notion of a prototype is relatively accepted and common. So this is a riddle that I had in middle school. I heard, you guys might have heard it too. A man and his son are in a terrible accident and are rushed to the hospital in critical care. The doctor looks at the boy and exclaims, "I can't operate on this boy. He's my son. How could this be?"
Female surgeon.
Right, yeah, female doctor, right, as opposed to doctor. The answer is that it's his mom, right? And when they did a study on this, when the riddle sort of first came out, looking at what different people thought and what different people assumed, they found that the majority of test subjects actually overlooked the possibility that the doctor could be a she, and that included men, that included self-described feminists, right? So this isn't something that people are doing because they're inherently trying to be mean or prejudicial or something like this. It's something about our stored representations and how we talk about them in the real world. And this affects what we can learn from the world. So when we're using a machine learning system and trying to pull from data in order to learn about the world, we're going to be subject to the kind of biases that are at play as we talk about the world and write about them in text. So this is an example from 2013, where looking at a bunch of news corpora, if you were to try and decide which was more common, blinking or murdering, you would decide that murdering was almost 10 times more common than blinking, right? Because blinking just goes without saying. It's something that's very typical. It's not really noteworthy. This is a problem known as reporting bias. So the frequency with which people write about actions, outcomes, or properties isn't a reflection of real-world frequencies, but it's actually a reflection of something else. Something like what people think is worth mentioning. So in a typical machine learning paradigm, we first start off with training data that's collected and annotated. From there, a model is trained. From there, media can be filtered, ranked, aggregated, or generated. And from there, people see the output. And we like to think of this as a relatively straightforward, clean system in machine learning. But actually, there are tons of data there are tons of biases just at the start before we even collect the data. So I talked about reporting bias, which is the way that people talk about subsets of things that are true in the world. There's also a similar kind of bias, selection bias, so the kinds of things you tend to talk about and focus in on. There's overgeneralization, there's implicit associations, there's stereotypes, there's prejudice, and this is all reflected in the data that we produce that gets mined by machine learning systems. And that's just in the data itself. Now, more different kinds of biases come in as we collect and annotate the data. So we sample things in disproportionate ways from different countries. For example, for a long time, a lot of the workers on Amazon's Mechanical Turk were in India, and that was a common way of collecting data in academia. We have sort of confirmation biases, where we tend to ask the questions and interpret the solutions as confirming our pre-existing beliefs. And these all affect what we end up writing about, what we end up learning, and what the machine learning system itself will learn. So here's some of the cognitive biases that come into play, both in the data and in the interpretation of the outcomes of the model. These are some that I found to be the most useful as I've been working on these issues. Not at all exhaustive. It has automation bias, which Emily mentioned a few times, which is the propensity for humans to favor suggestions from automated decisions over contradictory information from a person, and similar kinds of issues. I won't have enough time to go into really detail about all these biases, but just sort of the point is that they're rife. So instead of having this really nice end-to-end pipeline, instead we have human bias at the very start of the pipeline. This then gets propagated throughout the system. The machine learning algorithm will learn it, pick up on it. This is an effect of maximum likelihood estimation, which is very common in machine learning. And as people see the output and act on it, this creates a feedback loop that becomes the source of new biases in training data. So Emily, for example, mentioned the doctor image search example. What people click on, given that set, will then become new training data. And so if they were already given a skewed sample to click on, this now becomes skewed and biased again, which is now input again. So it's this feedback loop of bias that doesn't make the situation any better. So this is a bias network effect, or I like to call it bias laundering. It's important to say that bias can be good, bad, or neutral. So this term is often used to mean lots of different things. Marcus talked about it as, in the context of statistics and machine learning, where you have sort of the bias of an estimator or the bias term. There's cognitive biases, which I've just talked about, things like confirmation bias and recency bias. Also things like optimism bias, right? They're not always negative, they can be neutral. It depends on how they're applied. And generally when we're talking about bias in the context of machine learning, we're talking about algorithmic bias, which is something else entirely. And this is kind of an attempt at a definition. There's been a few, but here's one that I have found really useful to work with. Unjust, unfair, or prejudicial treatment of people related to characteristics, related to personal characteristics. And I thought The Guardian actually put this really nicely. This was back in like 2016, I think, where they said, Although neural networks might be said to write their own programs, they do so towards goals set by humans using data collected for human purposes. If the data is skewed, even by accident, the computers will amplify injustice. And I really keyed in on this amplify injustice message. I thought that this was one of the most important things to get right as we continue to develop machine learning systems. So this has come up already a few times, so I won't talk about it too much, but one of the areas that this really applies to is in predicting future criminal behavior. So it's becoming more and more common to predict police deployment locations, predict sentencing, and this is largely subject to overgeneralization errors, feedback loops, correlation fallacies. There's also an alarming increase in interest in inferring things from faces that really aren't rightly inferred from faces. This is something that humanity has sort of done as far back as I could find. 5,000 plus years ago, there was this idea of face reading. There was physiognomy in Greece, and that sort of has become a pseudoscience a few more times in history. And now it's happening again in the context of deep learning and machine learning. So there's an Israeli startup called Faceception that says that they have specialized engines for recognizing high IQ, white-collar offender, pedophile, and terrorist from a single face image, right? But they have clients, and their clients are Homeland Security, their clients are public safety, their clients are largely governments from other countries that are purchasing this kind of problematic and often biased software. They didn't describe how their system worked, but a similar system had been proposed in 2016 that I was able to kind of dig into and figure out, like, how is this working? Why are they saying that this is actually predicting criminality? And what I found was a lot of sources of confirmation bias and poor science. So, for example, they mentioned that they used less than 2,000 closely cropped images of faces. If you've worked with deep learning, 2,000 images is really not enough to pick up a signal of anything. And they used things like wanted suspect ID pictures, so pictures that were already kind of set up to look problematic. And they said some great conclusions, like the angle theta from nose tip to two mouth quarters is on average 19.6% smaller for non-criminals than for criminals. This is otherwise known as smiling, right? But when you're locked in confirmation bias and exciting headlines and this black box of AI, you're really pulled to kind of make these conclusions when they're not actually supported by what's happening. And there might even be much simpler things going on. This has come up again recently in work on predicting homosexuality. So this was work that came out of Stanford that claimed that they were able to predict someone's sexuality from a picture of their face. And they also had these great conclusions that were not at all supported by their work or their previous research, such as consistent with the prenatal hormone theory of sexual orientation, gay men and women tended to have gender atypical facial morphology. None of the people in this paper worked on prenatal hormone theory. This is just like something that sounded really exciting. But if you tear it apart and actually kind of look at what might be happening, a simple decision tree focusing on whether or not someone is wearing glasses, whether or not someone is wearing makeup, and how their head is tilted did just about as well as the accuracy of this apparent deep learning system that's learning something very deep. This says more about a difference in culture, in the presentation of the self, how people are presenting themselves publicly, and a lot less about something amazing, implicit, that only deep learning can pick up on. It's just that deep learning is being used as a tool to kind of launder biases, to kind of talk about stereotypes, and to kind of push through ideas that are fundamentally human ideas under some under some guise of objectivity. So that's an example of selection bias and experimenter's bias along with correlation fallacy. So AI can unintentionally lead to unjust outcomes. This is due to a lack of insight into the sources of bias in the training data and the model, lack of insight into the feedback loops, a lack of knowledge about subgroup-specific disproportional failures, which we'll talk a little bit about, and then human biases in interpreting and accepting the results. So even though a classifier has output a decision, that doesn't mean it's 100% right. Actually, it almost never means it's 100% right. And even when it does, the decision that you think it's coming to is not necessarily the decision that it is coming to. So one way that I've tried to move the needle forward towards being a little bit more transparent about the problems with machine learning systems, the disproportionate failures across different kind of subgroups, is this project called Model Cards, which is really similar to Emily's data labels. As she also mentioned, this sort of came around at the same time. It's just kind of like, in the air. And the idea here was that there's currently no common practice of reporting how well a model works when it's released. That's really weird. It's just common that we have machine learning systems made available through APIs, made available through commercial APIs, and there's not actually any information about how well it works with any kind of rigorous testing. And people just sort of use it and assume that it works, and that's not really what's happening at all. So one way to move forward on this is to actually provide transparent documentation alongside the model, talking about what it does, how it works, and why that matters. So digging into this a little bit, the basic idea here is to have model details, so the person or organization developing the model, as well as things like the license, where to send questions or comments about the model in order for the developers to further update the model as different users sort of see fit. Intended use, so this is the use cases that were envisioned during development, the primary intended uses. So to give an example of why this is important, for example, smiling recognition is often used as happiness recognition. Naively, if you just sort of have access to an API, it's really easy to make this mistake and say that these are two of the same kind of things, and then you take something that's been trained fundamentally on very surface level features and are now trying to say that it's something that's inferring inner emotion. And then this becomes deployed within further systems, such as software that tries to decide whether or not you should be hired, hire view. As well as other kind of factors you want to include. So similar to the data labels approach, demographic or phenotypic groups that the model is likely to affect, and ideally likely to affect differently. So this would be things like gender, this would be things like age, this would be things like Fitzpatrick skin type. And the metrics that would be reported would be metrics that are important to talk about how well the model works, but also to show how fair it is, how well it performs across the different subgroups, and how close those are to parity, whether there's much of a delta between them. Details on the evaluation data and training data. This ideally would have a pointer to data labels, data sheets kind of thing, so you could further dig in to where all the different sort of skews could possibly be. As well as quantitative analyses. So this should be both unitary and intersectional. So unitary focuses on single subgroups, so just looking at difference across gender, just looking at difference across age. Intersectional starts sort of combining them. So looking at the interaction of race and gender together, or age and gender together, and seeing how the performance works disaggregated in this way. And the cool thing about this is once you start doing the disaggregated evaluation across various subgroups, you're basically in the realm of fairness definitions. So a really common fairness definition is equality of opportunity, which is, for a classification system, equivalent to equal recall across subgroups. So if you're showing recall across subgroups in disaggregated form, you're also now speaking to modern day fairness definitions and how close the system is to meeting those. Alongside this could be things like ethical considerations and caveats and further recommendations. The quantitative analysis deserves a little bit more discussion just to kind of dig into this. This is actually a deployed system through Jigsaw. You can like write different tweets, different short messages, and it will tell you how toxic it thinks it is, and they actually have this up on their online thing now. They've launched some model cards where they take a look at different targets of abuse online and talk about how well the toxicity model works for those different kinds of individuals. using a score that is particularly suited for what they're measuring. So you can see that, for example, from their first release, they were doing very, very horribly, specifically on people who were black and gay, or text that had black and gay in it, and were able to make some substantive improvements simply by paying attention to this during development. So if nothing else, working towards disaggregated quantitative analyses is a great way of actually knowing whether or not you should be releasing this at all, where the disproportional failures might be. Okay, so that's basically the idea for moving from majority representation of people and data and everything else to something more like a diverse representation for more ethical AI. Okay, thanks.